Hello, this is Jennifer Martinez. In this video, we're going to introduce determinants. And I have here for a 2 by 2 determinant, if you recall from chapter 2, the formula is AD minus BC, denoted by determinant of A, where A is the following matrix, 2 by 2 matrix. Note, sometimes the determinant of A is denoted with these straight bars, like absolute values, but when it's a matrix, it will mean determinant. If you read the first paragraph of this section, it says that recall from chapter 2 that a 2 by 2 is invertible if and only if its determinant is non-zero. To extend this useful fact to larger matrices, we need a definition for the determinant of an n by n matrix. And we can discover this definition by looking at the 3 by 3 case, by watching what happens when an invertible 3 by 3 matrix is row reduced. So that's what we're going to do here. To discover the definition of a 2 by 2 case, we're going to write A in reduced echelon form, assuming A is invertible and A is not 0. So let's go ahead and do that. So the first thing I want to do is divide the first row by A. Then I'd like to get a 0 where the C is. So I'm going to multiply the first row by negative C and add it to the second row. So what you would get here is negative CB over A added to D. So I wrote it right there. I put the D first. Now we would like to get a 1 there. To get a 1, we would have to divide by this. We cannot have this expression to be 0. So we know that D minus CB over A, for this to be invertible, to get a 1, this cannot be 0. And if you simplify this, get an LCD, that would be AD over A, which equals AD minus BC over A. That cannot be 0. So I already assumed A was not 0. If it was 0, we might be able to swap the rows. If they were both 0, it could not be invertible. But assuming that A is not 0, you can see here, for this to work, for this to be invertible, the AD minus BC cannot be 0. So that is where we call this the determinant of A. So that's what they're going to do for a 3 by 3 case. I'm not going to do this, but I will show you where it is in the book, and we will go through it a little bit. Consider A to be this matrix. So really what they mean by that, I will write that, is A is A11. Notice the first entry denotes the rows. So this is the second row and this is the third row. And then the J denotes the columns. First column, second column, third column. So if we multiply the second and third rows by A11, so that's what they did here, A11, it's a little easier to get the zeros. So here you can multiply this by negative A21, for instance, and add it to that without getting the dividing and getting fractions like I did on the 2 by 2. So if we do that, they get a 0 here, and then this is where they get this term right here, right? Because it's A11 times A22, and then they subtracted A21, A12, and then so forth. You can see this is A11, A2. So I'm just going to work with this one right here, taking negative of this term, multiplying by row 2, adding to row 3, putting to row 3. So I just wrote here this. This is the third column of row 2, and then added to row 3, the new row 3 is going to be this times this. If you do all that out and multiply it, you're going to get A11 times this delta. You can kind of see it if you do it out. Like for instance, just the first term here, A11 times A23 times A32 is, where is it? Right here. Has an extra A11 in it, right? A11, A32, A23 has an extra A11 in it, but we're going to all factor that out and put it there. So if you multiply it and see that you get that there, that, believe it or not, is the determinant of a 3 by 3. Too complicated. So what they did is they wrote it. They changed the delta to be this. This is the same as that. So for instance, if we look at this, just the delta, we don't need that extra A11. We're assuming that's not 0, the same as before. That didn't matter. It's the, this whole delta cannot be 0. And if you're just going to take the determinants of these 2 by 2's. So this is A22 times A33. So it would be A11, A22, A33, which is this term. And then we're going to subtract these two. So it's A11, A23, A32. That's the one we're looking at. And then similarly, this one is A21, A33. It's a minus. There it is, with an A12. And then this one would be, because it's a minus there, and this would be therefore a plus, because we're going to subtract with that negative. It's going to be A11, A23, and A31. Plus, there it is. And then finally, this would be the last two, A21, A32 with an A13. And that must be the last. So that's the definition of the determinant, what we're going to see. And you can read the rest on your own if you want. And again, this is where A was this 3 by 3. There's an easy way of, the reason they wrote it like this is because if you look at the first row, that's where these are coming from. It's a plus, minus, plus on the first row. And if you cross these out, notice how this is the determinant. Right, we're taking the determinant of the remaining columns. And then if we cross, right, we take A12, and we cross and cross, you notice what's left is A21, A31, and A23, A33. And finally, you have an A13 there, and you cross the row and the column out of A13, what you have left is the determinant there. So it's a great easy way to remember a determinant of a 3 by 3. And you can see here that this is what they call the determinant. It says we call delta the determinant of a 3 by 3. So that is the definition. So I just rewrote it here in the other notation. Definition of a 3 by 3, oops, determinant, where A is that same 3 by 3. The determinant of A is written as A11, cross out, what's left over, put a minus A22, cross out, what's left over, with a 2 by 2 determinant, plus A13, and you cross out what's left over, and you take the determinant of that. In general, if you have something larger than a 2 by 2, that's the definition of what the book uses. So for n bigger or equal to 2, the determinant of an m by m matrix, written the same way as we wrote up there, right? So if you had 4 by 4, you would just add a fourth column and a fourth row. It has to be an n by n. is the sum of the n terms where you have A1J, so this would be A11, A12, A13 for a 3 by 3, and you would keep on going if you have larger, times the determinant of A1J, right? Where A1Aij denotes the submatrix formed by deleting the ith row and j column, just as this one here. So this is the determinant of A11, so you delete the first row, first column. This is the determinant of A12 by deleting the first row, second column, and so forth. And notice how they have the plus or minuses. It's all there. So let's look at example 1. So if I look at that so to find the determinant of A, or you can call it that's also another way to denote determinant of A. We know from this formula it's A11, determinant of A11, minus A12, determinant of A12, plus A13, times the determinant of A13. And again, this would be A11, here's A11, is 1, and the determinant, I'll just do this notation of A11, is I'm going to cross the first row and first column out, so I'll end up with 4, -1, -2, and 0. I'm going to put a minus sign, and then these do need to alternate. If you can see here, plus, minus, plus, and the next one will be minus, the next one will be plus. A12 is a 5. And then we're going to cross out that first row, second column, end up with 2, 0. That's the determinant A12, crossing out the first row, second column, and then -1, 0, and a plus A3, which is 0. Really doesn't matter what this is, but in case it's not 0, because 0 times anything is 0, that would be 2, 0, 4, -2. And if you figured that out, now these are all 2 by 2s, we know the answer of this. This would be 0 AD minus BC. Have a minus 5, 0 and a 0. Well, that's convenient. And then this is just 0. We don't need to figure that one out. So it looks like the answer is 1 times -2, because everything else is 0. And that's the answer. You're going to see from the next theorem, it really doesn't matter what row you choose. You do not have to choose the first row. So I could have said the determinant of A. I could have picked, oh, the last row. That looks nice and easy, because then I times the leftover determinant, which I realize doesn't even matter. But you have to get the signs right. Turns out the signs are going to be like a checkerboard. They alternate like a checkerboard. So the last column you would do plus, minus, plus. So that 2 is going to be a negative with a -2. Whoops, I didn't write it. Negative from the formula and a -2. And you'll see why in the next theorem. But if you're doing the second row, you would have to do minus, plus, minus. So it's all a checkerboard. And we're going to do what's remaining there. And again, the last 0, it really doesn't matter what it is. But I wrote it anyway, just so you can get the formula. So you can see this is going to be a 2, and then AD minus BC, same answer. So I think I'm going to end here with my first video. You can continue with the second video to see the theorem that shows that you can do any row. And by the way, you could do any column too. So stay tuned.